started talking without realizing that the mic was off. So we'll start again really quickly. So the first thing we need to realize is that everything is made up of, all materials are made up of things called atoms. Now, you're familiar with this because you guys have come across this many, many, many times in your GCSEs. So all matter is made up of atoms, and an element is a particular type of atom. Sorry, elements are different types of atoms and they exist in the universe. Now, compounds are more than one type of atom that are chemically combined. In other words, they are bonded. They are bonded in some sort of way. And then mixtures are more than one type of molecule that is not chemically combined. In other words, they are not bonded together. They just exist in the same space. Now, when we talk about the atom itself, let's start with there. It's developed over time. The idea of atomos came from a guy called Democritus in ancient Greece, but it wasn't until much later that the idea came about of matter being made up of things that could not be divided any further. And we'll talk about the people that were responsible for this. The next model that came across, or people came across it, was the plum pudding model. Now, the plum pudding model is essentially was after the discovery of electrons, and we'll talk about that later today. And then you had the nuclear model, which the big jump was that you now had something called a nucleus, and then finally you had the Bohr model, which you now have. If you notice between the nuclear model and the Bohr model, the key difference is the electron shells. And like I said, we'll talk about that in a bit more detail today. So let's have a look at this then. In early 1800s, the idea of atoms was first promoted by a man called John Dalton. He carried out experiments that led to the idea that atoms were tiny spheres that could not be divided any further. Um, that was quite revolutionary at the time because the idea that you could get down to the smallest matter was quite big. And then it wasn't until the end of the 1800s when J.J. Thomson carried out an experiment which discovered electrons. Now, electrons, these things here, if you think of, say, for example, a cupcake, if I said draw a cupcake, um, if I said draw a cupcake, you would pretty much draw a very simple cupcake that looked like this. Now, if I then said, right, okay, great, but what we need to do is we need to, the cupcake has chocolate chips in it. You wouldn't necessarily redraw the cupcake. You would just add the chocolate chips onto the cupcake, and that's kind of what's happened in this situation. J.J. Thomson, sorry, has gone from being a model of atoms where they were just kind of balls to now having electrons in. But you've got a couple of issues. First of all, the electrons were negative, and he knew that they were negative based on the way they behaved interacting with magnetic fields, etc. So if the electrons were negative, but the atoms overall were neutral, that means that the dough must have been positive. Okay. And so he came up with the idea of the plum pudding model. Now, I appreciate that not many people eat plum puddings anymore, but plum pudding essentially was, if you think of it, if kind of think of it like a ball of cookie dough. The ball of cookie dough was the dough itself was positive, and the chocolate chips inside the cookie dough were negatively charged electrons, and that was kind of his big idea. Now, the next guy was called Rutherford, and Rutherford. Oh, sorry. Yeah. You can take a screenshot, but I have got a summary of this a little bit later. So Rutherford, he did an experiment. He took some alpha particles. He didn't know what they were. He just took these positively charged particles. Alpha radiation had been discovered, and he fired it at a beam of electrons. Sorry, a beam of alpha particles fired at some gold foil. When he fired this at cold foil, what he expected was for most of the alpha particles to just go straight through. He wasn't expecting anything else. And so if you think of a ball of cookie dough and you've managed to get yourself hold of a really, really powerful BB gun, then what's going to happen? Well, ultimately, most of the BBs, most of the bullets will just go straight through the plum pudding or the cookie dough, whatever the situation might be. Okay, so I'm going to show you an animation of what he expected to happen. So if I turn on my alpha particle source, and you can see that what should happen in theory was that all the alpha particles just go straight through. Then none of them deviate, none of them kind of move around, etc., etc., etc. So that's what he expected to happen. However, this is what actually happened. When he fired it, he noticed that, and I'm going to turn the tracers on so hopefully you can see them. When he fired it, he noticed that not only did some of them get deflected, but some of them actually, and if you wait for it, you might see one. If you focus on one of the atoms, you might see one. Some of them actually bounced backwards. They deviated, they were deflected by more than 180 degrees. And so you saw that one just come back from the top left. Oh, one from the top right is just come making its way back now. And that happened very, very rarely, but it did happen. So Rutherford had to rethink the model of the atom entirely, and that's kind of what he did. So he had three main observations. His first observation was that most of the alpha particles just went straight through the gold foil. So his conclusion was that most of the atom is empty space. His second observation was that some of them were deflected by small angles. Now, if you think of it, the two positive particles, if you have two magnetic north poles, and I'm sure you've done this as a kid or in school, if you, as soon as you bring two magnetic north poles together, they're going to repel, and that's what was happening. So he concluded that the nucleus was positive. And then finally, very few were deflected backwards. So the conclusion he drew from that was the nucleus is small, it's dense, and it's massive. Massive, not really big, but massive in terms of most of the mass of the atom is concentrated inside the nucleus. Now, this is a typical 6-mark question, right? They love asking this particular question. What was Rutherford's experiment, and what were the observations, or what did Rutherford's experiment conclude? And these are literally the 6 marks. It's what was the observation, and then link it to what was the conclusion. And that's how you would get your 6 marks from that particular question. The other thing that they might ask is a comparison. Oh, let me get rid of the ink. A comparison between the nuclear model and the plum pudding model. So if I had to look at the plum pudding model, I'd say, right, okay, so the plum pudding model, you've got no nucleus, you've got electrons embedded in the dough, and the overall charge of the atom was positive. However, if you look at Rutherford's model, you've got a distinct nucleus. Oh, let's skip ahead. You've got a distinct nucleus, you've got electrons kind of floating around the outside. Notice he didn't have any idea as to where the electrons were or what they were doing. He just knew that they weren't inside this thing called the nucleus. And the nucleus is positive. Now, that wasn't the end of the story. Niels Bohr later on discovered what actually happens with the nuclei, with the electrons. So he discovered that electrons orbit the shell at particular distances. Electrons are arranged in a shell patterns. Now, later on, it wasn't in that same experiment, but they discovered that, and as this is as far as you need to know for GCSE, for A-level, this is going to be slightly different. In the first shell, you've got 2 electrons maximum. In the second shell, you've got 8. In the third shell, you've got 8. And in the fourth shell, you have got more than 2. But for the AQA spec and for Edexcel, you only need to know the first 20 elements. So based on that, you won't need to know the electron structure of the elements after that. So he came up with this model. Now notice on the first shell, I've got 2. On the second shell, I've got 8. And on the third shell, for this particular element, I've only got 1. Okay, so this would be an atom of sodium. Now, later on, it wasn't for a while actually, where the neutron was discovered. Now, the neutron was the last particle to be discovered. The reason being is it hasn't got a charge, so it's very, very hard to detect. But if you think of an atom, again, go back to the model of two magnets being pulled towards each other. If you've got a positive charge, two positive charges, and they're brought closer together, they're going to repel. So why doesn't every atom just fly apart? Because there's another force called the strong nuclear force. Again, this is above your GCSE. You don't need to know it per se, but hopefully it gives you an idea. Now, the strong nuclear force only acts at very small distances. So actually, if you've got 2 protons and 2 neutrons, they are all being attracted to each other, and the neutrons are there to provide a stabilizing force. They hold the nucleus together, and that's one of the key things that you kind of hopefully gives you a better idea of what is actually happening inside the nucleus. So this was the final model of the atom that, as far as we're concerned, is what we're going to go with. So James Chadwick in 1927 discovered neutrons. So now we've got protons, we've got neutrons, we've got electrons floating around in shells around the outside. So this is kind of the summary of all of them. In the early 1800s, John Dalton came up with tiny spheres that could not be divided. Then in the 1890s, J.J. Thomson discovered electrons and therefore came up with the plum pudding model. Let's change the pen. Came up with the plum pudding model. And then we had, then in the early 1900s, we had Rutherford. Rutherford, Geiger, and Marsden were the 3 people that conducted the experiment. Geiger and Marsden were kind of PhD students at the time, so they did not get much credit for it, unfortunately. But Rutherford came up with the alpha scattering experiment. Some people call it the gold leaf experiment. Came up with the alpha scattering experiment, which talked about the nuclear model with the nucleus in the middle. And then you had the Niels Bohr, who came up with electron orbitals. So the idea that electrons orbit nucleus at specific distances in shells was Niels Bohr. And then the final one was sorry, I didn't mention this actually. That's a good point. Positive charge nucleus could be subdivided into particles of positive charge. So protons were discovered by a slew of people, a group of people, and the way that they were discovered was, if you think of you go to a shop, and every time that you go to the shop, you always get your change in denominations of 10. So for example, 60p, 10p, and 50p. And what they noticed was every time they did the experiment, they always got this a denomination of a charge. So it was always a multiple, whatever the charge was of the nucleus, it was always a multiple of the same number. And therefore, what they decided, or rather what they worked out, was that there must be a positive particle with a particular charge. And that positive particle was then called the proton. Yeah. Now, finally, it was James Chadwick, and James Chadwick discovered the existence of neutrons. Now, well done to Zach. Now, in terms of, so the next part of this, the next part of the, ladies and gents, is the kilogram. So when I say the kilogram, I mean there's a museum in France, and it contains the kilogram. This is the kilogram, which then other countries compare their version of the kilogram to, and that is how we make sure that everything is the same. Now, ultimately, that is quite an old-fashioned way of doing it. So we came up with a definition for what the kilogram should be. It's 1 decimeter cubed or 1 liter of water at 3 degrees Celsius. Now, why is that important? Because we need to have something. So the idea of the kilogram is to have a comparable mass with which we can take all other measurements from, right? So if you look at a proton, the proton, its actual mass is 1.672 times 10 to the power minus 27 kilograms. Similar with the neutron is 1.675 times 10 to the power minus 27, and then the electron is very, very small. 0.000911 times 10 to the power minus 27 kilograms. So if you look at the first two, the proton and the neutron, they're very, very, very similar. Now, when you're doing calculations when it comes to masses of atoms or elements or whatever it might be, you don't really want to work in powers of 10 to the power minus 27. So what they do is they just call them 1. And we can call them 1 because they are so similar, and that's why it's called relative mass. So it's comparing the mass to a single proton or a single neutron. And the electron is so small that we can actually, when it comes to measurements of mass, we can just ignore it. We know this because if you think of going to the airport, if you had, say, for example, a weight limit of 30 kilograms for your luggage, if your weight limit, if you're kind of on the scale, it said 30.0001 kilograms, the attendant isn't going to care. So therefore, it is with electrons, we can say they have almost zero mass or negligible mass. When it comes to charge, again, it's a very similar kind of scenario. We know that a proton, or rather a proton, has a charge of +1, an electron has a charge of -1. The actual charge of a proton and electron is 1.6 times 10 to the power minus 19 coulombs. Now, that mass, that charge, sorry, is, rather than say 1.6 times 10 to the power minus 19 every time, you can just call it plus or minus 1. Now, okay, great. So what does that mean in terms of our atom? So we've got 3 subatomic particles. Those subatomic particles are protons, neutrons, and electrons. Now, the mass of a proton and a neutron we've already looked at, and its relative atomic mass is 1. And the mass of an electron is very, very, very small. So this is negligible, almost negligible. Almost 0. Now the charge of a proton is +1, the charge of a neutron is 0, and the charge of an electron is -1. And the location of them, so the protons and the neutrons are found inside the nucleus, and the electrons are found on the shells. The problem is that, having done this for many years, students always confuse which way round these things go. And so therefore we need to come up with a way to try and remember it. So the way that I came up with it, and yes, it does sound a bit silly, but P ni EU or P ni EO, P ni EO, P ni EO. Just keep saying it in your head. P ni EO. Proton has a mass of 1. Neutrons have a mass of 1, and electrons have a mass of 0. So P, N, E, O. That's the way I remember it. The other one is Peter Piper eats nuts, never zebras. Peter Piper eats nuts, never zebras. Peter Piper eats nuts, never zebras. So how do I remember, what is that linked to? Protons are positive, electrons are negative, and neutrons have a charge of 0. Peter Piper eats nuts, never zebras. Yeah? So that's kind of a couple of ways to try and remember this. Now, the nucleus is very, very small compared to the rest of the atom. It's about 1/10,000 of that of the atom. So very, very, very small. And we talked about this already. The first shell can hold 2 electrons, the second shell can hold 8, and the third shell can hold 8 as well. So what does that look like? In the chemical symbols in the periodic table, what you'll have is a mass number given to you and the atomic number. Now, the mass number and the atomic number give us pieces of information, and you are expected in the exam to draw from that and pull out the information that it gives us. So the mass number is the total mass of the atom. Now, we know that if the mass number is 16, protons have a mass of 1 and neutrons have a mass of 1. So actually, the mass number is going to be equal to whatever the number of protons is plus the number of neutrons, because each of them have a mass of 1. When we talk about atomic number just tells us the number of protons. So how do I remember that in the exam in a high pressure situation? I remember the phrase ape man. So what have we got so far? We got P, Ni, EO. We've got Peter Piper. Peter Piper eats nuts, never zebras. And then we've got Ape Man. Now, Ape Man is the atomic number, whatever the atomic number is. So if I've got an atomic number of 8, is equal to the number of protons. And again, so that's the number of protons, 8 protons, is equal to the number of electrons. So I've got 8 electrons in the oxygen atom. So let's just write this. Protons, I've got 8. Electrons, I've got 8. The only particle I'm missing is the number of neutrons. So if I take this equation here, mass number equals proton number plus neutron number, I can rearrange this. So just bring the number of protons over to the other side. So mass, take away the atomic. So 16, take away the atomic, which is 8, is going to give me the number of neutrons. Now, this hopefully, apologies if I'm going really slow over this, but this is one of the things that students confuse so often in the actual exam. So just please remember ape man, P, Ni, EO, and Peter Piper eats nuts, never zebras. Now, once you've got that down, the next thing that we need to get our heads around is the idea of isotopes. Now, isotopes are different atoms of the same element. So what do I mean by the same element? Well, they've got the same number of protons, and that's what defines an element, is the number of protons, but they have different numbers of neutrons. So they've got the same atomic number, but different mass numbers. Same atomic, different mass, same number of protons, different numbers of neutrons. So if I take hydrogen, these are all hydrogen atoms. Hydrogen has 1 proton. Deuterium has 1 proton and 1 neutron. So its mass is actually 2. And tritium has 1 proton and 2 neutrons. So its mass is 3. So what does that look like in terms of symbols? Well, hydrogen will just have a symbol of 1. Deuterium will have a symbol of 2. Sorry, mass number of 2, and tritium will have a mass number of 3. The atomic number stays the same. Now, what you might notice in the periodic table is some of the mass numbers have a decimal point next to them, which makes absolutely no sense. If you Google the periodic table right now, you will see, I don't know, 18.01, and you can't have 0.01 of a neutron or a proton. So where does that number come from? So this is for the higher tier, and this is what you need to get your head around. The relative atomic mass is the average value that takes account of the abundance of the isotopes. So if I've got 2 different isotopes of an element and they are relatively abundant, so not like 99.9% and then 0.1%, I mean like 25% and 75%, to work out the average mass, it's a very simple situation of percentage of isotope 1 multiplied by the mass of the isotope plus percentage of isotope 2 times the mass of the isotope 2, and then you divide that by 100 to get the average mass. If you've got multiple, then you just do the exact same thing. You just multiply all the percentages and then you divide by 100 to give you your average mass. So boron has 2 naturally occurring isotopes. It's got B10, which is 20%, and B11, which is 80%. Now, the number after that tells us the mass, and the percentage in the bracket tells us the abundance. So how do I work this one out? Well, I've got a mass of 10, and the abundance is 20%. So I'm going to times that by 0.2. and then I've got the second one has a mass of 11 and it's got an abundance of 80%. So I times that by 80, and then I have to divide that by 100. So I'm going to have 200 plus 80 times 11. So we're looking at 880 divided by 100. And I should get an answer. If I plug that into my calculator, I should get an answer of 10.8 or 11. So if I was to write this on a periodic table for GCSE level, I would just use the mass number of 11. If you go beyond that, then obviously you need to have to one decimal place. So that's something that you might be asked. They will either specify how many decimal places. If they don't, then go with one decimal place or two decimal places to give you the best answer. The next question is magnesium has 3 naturally occurring isotopes, Mg24 times 79%, Mg25 and Mg26. Okay, so we've got 3 isotopes this time, but all we have to do is the exact same thing. So we're going to do 24, which is the mass, because it tells me straight after, times 79%, close bracket, plus I've got magnesium, which is 25, multiplied by 10%, and I've got magnesium 26 times 11%. And then I have to divide all of that by 100. And if I plug that into my calculator, I should get an answer. The answer that you get when you plug all that in is 24.32 or 24. Now, again, if I was given this in the exam and this was a relative abundance question, I would give 24.32 as my answer. Just to make it absolutely clear to the examiner that I know what I'm doing. Right. Now, the last bit of this is understanding the electron configuration. So we said previously that when it comes to atoms, the number of electrons that can fit onto a shell are predetermined. So you can have 2 on the first shell, you can have 8 on the second, 8 on the third, and then 2 on the final shell. That final shell of having 2 is only because you need to know up to the first 20. So you could be asked to draw the electron configuration of the first 20 elements. Yeah. Now, sorry, the electronic structure. The electronic configuration is a slightly different thing. The electronic configuration tells us how many electrons are in each shell separated by a comma. So for example, if I said oxygen has 8 electrons, then the first shell can only have 2. So if I have 8, I'm going to have 2 in the first shell. How many have I got left over? I've got 6. So therefore it's going to be 2, 6. Right. Now, the answer for the first one was 28, second one was 22, and then the final one was 287. So hopefully relatively straightforward. You just got to look at how many electrons can fit in each shell and just put them down with a comma between them. Now, in terms of, let's do another happens today's, but we'll go from there. Right. I'm conscious of time, so we've only got 5 minutes left. So I'm going to not rush through, but I'm going to talk through the last bit relatively quickly. So obviously Dalton came up with the idea of last bit is looking at the periodic table. Dalton came up with the idea of kind of atoms, and he just arranged them by atomic weight. And the early periodic table was incomplete. Some elements were placed in inappropriate groups, and it just didn't work. Then the next person to come along was Dobronier. He came up with the idea of law of triad. So he grouped elements into groups of 3 based on their properties. And as you can see, that didn't quite always work either, especially with some of the heavier elements that were being discovered. In 1864, John Newlands then started to put them into groups of octaves, so in groups of 8. Again, this was working relatively well for a lot of the elements, but it didn't quite work for all the elements, especially as you got further down the line. And it wasn't until 1869 when Dmitry Mendeleev is credited as having come up with the periodic table. He put them in order of kind of not only group them in order of mass, but also group them in order of properties. So this is the key thing. Dmitry Mendeleev's big idea was to put them in order of mass, but also to put them in order of their properties. And based on that, he could predict the properties of undiscovered elements. So he left gaps for elements that hadn't been discovered yet. And it was that allowed him to then be like, right, okay, when elements were discovered, he could predict, this is what their properties would be. And actually, it turns out that he was correct. And when he was correct, it really kind of hit home in terms of the idea that his periodic table was very likely to be the most accurate one. So Dmitry Mendeleev, he arranged them in order of their mass and in terms of their properties, and he left gaps, which meant that when elements were discovered, he predicted the properties of them correctly. And then it wasn't until 1913, a little while later, when Henry Moseley came up with the idea of the periodic table as it looks today. And this kind of was the history of the periodic table. So if you look at the elements on the board, the names on the screen, what you'll see is that Dalton put them in order of increasing atomic weight. Mendeleev put them based on their mass as well as their properties. Newlands based them on groups of 8 on repeating patterns of property, and Dobronier put them in groups of 3. So this was called the triads. Law of octaves was Newlands, and then the periodic table was Mendeleev. That's kind of the overview. I know I'm rushing it slightly because of time, but that is the broad overview of what the history of the periodic table looks like. You might be asked about Mendeleev, comparing him to Newlands. So the key thing was Mendeleev did mass and properties. Why was Mendeleev believed over, say, the others is because he predicted the properties correctly, which led to the discovery of the element. And then finally, when it comes to the periodic table, the individual rows are called the periods. Now, sometimes in the periodic table that you guys will have, the hydrogen is placed in the middle. So the easiest way to count the periods is on the right hand side. So you just go 1, 2, 3, 4, 5, 6, and that's how the easiest way to count the periods. Some people, because hydrogen's in the middle, some people start labeling it from the left, and you're obviously off by 1. The other thing that you need to know, and we'll look at in later lessons, is the groups. So the groups are the columns going down, and elements in the same group have similar properties. Elements in the same group have similar properties. That is really important, and we'll look at that again in a future lesson. Right, I'm going to stop there. Thank you very much for your time and attention. Take care. Bye.